to start. Now we have Thomas Burton, who's a biomechanical engineer. He'll be presenting on a comparison. Oh, forgot my sheet. I'll let Thomas tell you what he's doing.
All right, first of all, thanks for coming out, guys. It's great to see so many people interested in 3D printing, so hopefully it can address some questions you may have. So my name is Thomas Burton. I'm representing Boundless Bracing. And I'm going to talk about a comparison of material properties in OMP. More specifically, we're looking at multi-jet fusion 3D printed materials versus traditional thermoplastics. Before I get started, I just want to give a quick thank you to Victoria Champion. She's not at the conference today, but she was very influential in grabbing the data for the material properties we're going to present and getting the presentation together. A quick disclaimer, project funded by Boundless Biomechanical Bracing, and within the clinic we do use the multi-jet fusion printing in-house. We also have an FDM printer that we use as well. Okay, so why do we think this is an important topic? So whether you have extensive experience with 3D printing or just starting out, or just beginning to learn, it's really easy to get engulfed in one, the types of printing that are out there, and two, the types of materials that are available for each printing process. So the speed at which the technology moves is extremely fast. So what we want to do with this presentation is kind of take a step back into how are these materials really acting, and how do they fit in a process's or orthotist's day-to-day decision-making when designing an assisted device. And lastly, how can these materials be leveraged as a new tool within a clinician's toolbox to hopefully have improved outcomes for their patients. So not only the material, but the type of 3D printing process that is used can have great impacts on the mechanical properties of the end device. Many may be familiar with the most common type of 3D printing in FDM printing, or fused deposition modeling. And that's the printing process on the right-hand side of your screen, where a filament is extruded through a heated nozzle and laid down layer by layer. The main disadvantage of this printing process is the strength between the layers, so the orientation of the part within the print versus the loading conditions that are applied will greatly impact the mechanical properties. So today we're going to focus on multi-jet fusion, or MJF process. It has been shown to have high strength and near isotropic properties. Has also been proven within OMP over the last 3 to 4 years to produce high quality end use devices. So just a quick overview of what the multi-jet fusion process is. So MJF is a powder-based process, so all the materials that we're going to talk about are in their raw powder form, and they live in the brown box that you can see on the screen. The materials get sucked through the processing station, which is in the middle, and extracted into the build unit, which is on the right-hand side of your screen. The build unit then goes into the printer, which is on the left-hand side, where liquid agents are deposited onto the powder, where the part is to be solidified under high heat. So what we did was we took a deep dive into the literature to find mechanical properties of thermoplastics that we normally see within the clinic, and compare them to the 3D printed materials that we can see on the multi-jet fusion platform. So on the 3D printed side, we mainly explored PA11, or nylon 11, PA12, again a form of nylon, and thermoplastic polyurethane, or TPU. I noted polypropylene on this list. So polypropylene was just released on the newer 5200 version of multi-jet fusion printer. We left that out of this analysis because there's not a lot of data on it, but it is available on the newer multi-jet fusion platform. So to characterize these materials, we looked at 5 main material properties. The first being percent elongation, or a measure of how ductile the material is. Flexural strength, which is very important for what we mainly see at Boundless for AFOs. Tensile strength, Young's modulus, or a measure of how stiff the material is, and density, which will give us an idea of what kind of weight reductions or weight gains we would see from the 3D printed materials. That I'll go over in just a second. So the first property we looked at was percent elongation, or the ductility of the material, and that is measured by a tensile test and measuring the amount of deformation that the material has undergone. So for each of these graphs, the blue bars represent the traditional thermoplastics, the gray bars represent the 3D printed materials, and then you also see an orange dotted line, and that is the standard deviation between the values that we found. So the first property, percent elongation or ductility. So what we found was that PA11 was very comparable to the copolymer, whereas PA12 was very comparable to the ProComp material. And then lastly, the TPU had similar properties to the low density polyethylene in terms of how ductile the material is. The second property we looked at, flexural strength. So it's the ability of a material to withstand forces applied in a perpendicular direction. So the loading situation that we generally see in an AFO. So for flexural strength, we found PA11 and PA12 exhibit properties most closely to ProComp, and TPU again was a little bit of an outlier in this category, but was most closely related to the copoly and the traditional thermoplastic. The next result is density. And there seems to be a lot of talk about 3D printed devices are always lighter. And I'm going to touch on a second on what we see from the results. So we can see when we evaluated density that all the 3D printed materials are actually denser than the traditional thermoplastics, other than the polynylon, which is in the middle of the screen. So the PA11, all of the densities for the thermoplastics are very, very similar because they're all polymer based. So the very low deviation between the traditional thermoplastics and the 3D printed. However, 3D printed is definitely denser than a lot of the thermoplastics we see. I do want to note that in the 3D printed devices, within Boundless, we generally see the 3D printed devices are a little bit lighter for the most part, but there's mixed results for that. But keeping in mind that most of those weight reductions that we could possibly see in a 3D printed device is because of design, not necessarily the material properties of that specific material. The next result we looked at is tensile strength. So that's the strength of a material breaking under tension. Again, that's evaluated from a tensile test. In terms of tensile strength, we found that PA11 was very similar to polynylon, as well as PA12. Again, very similar to polynylon. TPU in this category was, again, very similar to the low density polyethylene. The last property we looked at is Young's modulus, or the stiffness of a material, and that's represented by the stress-strain relationship of a tensile test. So stiffness of the material, we found PA11 and PA12 were very similar to a ProComp, and again, TPU very similar to a low-density polyethylene. So main takeaways, we found that TPU was very comparable to a low-density polyethylene in the categories that we evaluated. However, it is a little bit heavier and not quite as stiff as the low-density polyethylene. The 3D printed PA11 and PA12 exhibit very similar properties to a ProComp. However, they're slightly denser, have increased tensile strength, flexural strength, and percent elongation at break. So the 3D printed PA11 and 12 were a little bit more ductile than the ProComp material. So what does this really do for us? So knowing the mechanical properties, we can start to perform finite element analysis and predict the properties of our end devices now that we have a clear picture of what those 3D printed mechanical properties are. We can make informed material selection, so that reduces the amount of prototype time that we need to complete. So orthotists and prosthetists can determine where those 3D printed material properties fall within the traditional thermoplastics and compare those properties before going to a 3D printed device. And we can also start to optimize weight of devices, so relieving areas of low strain and adding thickness to areas of high stress, and creating obturators and things like that in areas of low stress. With that, open to any questions, and thanks guys for listening.
Questions?
Did you give any thought to testing them for repetitive stresses? Because you just did a one-off, like a comparison of material only, not under continuous load or continuous stress.
Yeah, so fatigue is something that we're looking at that requires extensive mechanical testing. Unfortunately, with 3D printed materials, there's not a lot of studies out there that actually do life cycle tests of thousands and to a million life cycles. So it's one of the limitations really within the literature as a whole. So it is something we were looking at, testing those 3D printed materials and how they withstand under cyclical loads, but there's just not a lot of information on it so far.
Yeah, that's one reason why I asked the question. The other
Yeah.
one was adjustability of the material or deformation. So if a person was to adjust a 3D printed device, for instance, it automatically deforms the structural integrity, from what I understand, whereas the other materials, they tend to be a little more user-friendly, if you will.
Yeah, so the 3D printed materials, as far as adjustability, we mostly prototype with PA12. As far as adjustments with heating and flaring out different areas, it's pretty welcoming of those adjustments. It does change the mechanical properties a little bit. Again, very little literature on what those changes actually are. The TPU, however, is not great for adjusting afterwards. If you heat it up, it tends to kind of just flare and break. One thing that we are looking to doing is vapor smoothing the TPU. It's a separate process after printing, but it seems to strengthen the mechanical properties of the material, and the adjustability after is a little bit better.
Okay. So from what I understand, and I could be wrong, the inner structure of 3D printing is essentially a honeycomb like formation, is it not? Matrix sort of thing?
Depends on the design. For most of the devices we do, they're solid plastic.
Okay.
Especially for rigid, hinged, and ESR AFOs that we normally see, they're solid. If we do something like a heel lift, it's like 4 centimeter, 5 centimeter heel lift, we have an option to create a lattice structure inside of it to reduce the weight of it. Because multi-jet fusion is powder based, we can really have a whole design freedom within the process. Yeah, but most of the devices we do are solid structures.
Just to add on to that, the most commonly known style of 3D printing, like FDM printing, that's where you'll usually get the plastic like honeycomb interior, automatically with most slicer softwares, but a major advantage of that multi-jet fusion is the ability to have like really solid and fuse layers so that you don't have those striations.
Okay. When you were mentioning that statistically you found it to be a little bit lighter than the traditional plastic, I was just under the assumption that it's because you're using less material in terms of volume, but that's not. So where's the lightness coming from?
So the lightness would come from adding obturators in areas of low stress, or adding holes in the back of the devices. I wish I brought some samples with me, but I don't have them. But yeah, it's more a design of the holes rather than the internal structures within the plastic.
I could add to that. A lot of times it's just creating corrugations or reinforcements, stuff that you can really easily do digitally, but hard to do with conventional thermoplastics. If you come by the booth, you'll see, and it's isotropic, right? It's like solid material, so it's easy to flare, easy to grind, and it's really no different than it is a thermoplastic, right? So I find it works really well. Cosmetically, you can see it. As soon as you grind or buff, you can see like that matte finish is disturbed. But functionally and working with material, it's very similar to flaring thermoplastics.
We do have a sample that has been flared out and grinded and buffed out, so we can show you that too.
There's a question in the back.
Multi-jet.
Sorry.
Multi-jet printer. How long are you typically taking to print an ad AFO?
Sorry, how long does a print take?
Yeah.
Yeah, so it's all based on the build height. So if we have a full build height, it doesn't matter how many AFOs or how many devices are in it. The length of time that it takes to print is always the same based on the build height. So if we do a full build, it can take between 17 and 20 hours to print, and then up to 30 hours of cooling time, because the plastic is basically a molten, in its molten state once it gets fused. So it does take a long time to cool. We do have the option of fast cooling, so you can fast cool the material up to about from 30 hours down to about 10 hours. It just depends on the part geometry that's in the build. If there's any parts that are long and thin and you try to fast cool it, they tend to warp. So it's a constant kind of battle of how quickly can we cool these parts while still maintaining the integrity of the part.
So you have your patients wearing them? They're wearing them now?
We do. So it's more of a large scale R&D project. We have a poster on it if you wanted to check it out. So when we dispense 3D printed devices, they're side by side with the traditional device as well. And we will get patient feedback. We're using the Quest patient satisfaction score. So we'll get feedback at 4 weeks, once they've had 2 weeks to wear their traditional and 3D printed. And then we'll also follow up at the 6-month mark to see if there's any changes. Are they in their 3D printed brace full time? Do you like one or the other? Did they throw the 3D printed away and go to the traditional? So we're trying to get long-term patient feedback, and that's one of our main R&D objectives right now with the 3D printing. Yeah.
Okay. Hey, any other questions? No? Okay. Thank you very much.